Hello everyone. So welcome back to the channel. Today we'll be diving into the foundation of computer vision and object detection. That is one of the topic that seems intimidating at the first time, but once you get into the core, everything else will be deep learning based vision only. We'll not go into the robotic part. Okay, we'll be covering it into the not going towards the hardware side and everything, and not towards the environment side in the ROS part that we'll be see in upcoming lectures. But before that, we'll be only focusing over the computer vision part. Okay, so this is the introduction video. We'll be covering about computer visions and object detection. So let's start with the basic computer vision or CV. It's basically a teaching machine that looks at the image, video, and actually understand what's going on in that. The same way the human glance at a scene and instantly know that objects are there or not. Now, object detection is a specific task inside computer vision, and it's a step harder than simply classifying it. Classification just answer one question: what is in this image? And if you get a one label for the whole image, but detection asks how much harder, what objects are present, what exactly they are, and everything about that. So it's like a difference between computer vision and the object detection. So what you need to just remember is that classification is just one label per image, detection is multi-label plus location per image. Okay, that's what make detection a structural prediction problem. It's harder because you're predicting multiple things at the multiple location. Now, how does this matter and what are the real world uses for that? Okay, so first of all, the self-driving car that is being used in the detection of the pedestrian and other vehicle, traffic signals, boundary lanes, and everything. Second is the drones and the UAVs. Okay, you use the detection for obstacle avoidance and to localize the target or packages. Then we have robotics. If in a robotic arm need to grasp a object, it need to know precisely where the object is. Then we have the surveillance and the retail analytics. Think like counting people, detecting intrusions, and the monitoring self stock. Okay. Then for the medical imaging, this is one of the important domain where computer vision has taken a place. Okay. So now in the radiopathy, you can see that mostly in medical side, computer vision is being used. Okay. Now we have three important terms, that is classification, detection, and the segmentation. Okay, so before moving into further lectures, we'll get an idea about that. First one is the classification, that you give you a single class label for the whole image and that's it. Next is the object detection, that gives you a class label plus a boundary box for every object that work over this region level. Okay, now third part is the segmentation. Okay, now segmentation has been divided into two parts, semantic segmentation and the instant segmentation. So the semantic segmentation give you a class label for every single pixel. So instead of a box, you get a precise outline, but it doesn't tell you which instant each block belong to or pixel level. Okay, so no instant ID. Now instance segment, this is more detailed. Okay, class label plus a mask for every individual object instance, pixel level with the instance ID. Okay, now moving forward towards the image basis, that is the pixel, color space, and the channels. A digital image is just a discrete grid that sample a continuous real world scene. Mathematically, a color is like a tensor. Think of it like a 3D array with dimension, height, time, width, time, and the channels. H and W are just the height and width in pixels, and C is the number of channels. Pixels are the smallest unit of images. Each pixel stores an intensity value. If it is a grayscale, that's just a number per pixel. If it is color, then it's a vector of number for one channel typically. They are quantized into 8 bits, meaning values from 0 to 255. Now channels. Think of channels as one of the layer of intensity. What it does is that spam the entire image, a standard RGB image, as a 3 channel, red, green, blue. A grayscale image has just one channel, and some specified sensor or task added extra channels like the depth, infra, and alpha channel for the transparency and all. So the color space, this is basically the different way of representing information. One is the RGB. Okay, so it's the standard activity additive primary colors that is being used in the most of the CV data sets. Then we have the grayscale, just a single luminance channel, commonly used in the edge detection and everything. Okay, now we have the HSV. Okay, it stands for hue, saturation and the value. This separates color information from the brightness, which make it great for the color based segmentation and more robust to the lighting change. Then we have the YCBCR. It separates luminance meaning brightness from chroma meaning color, and this is the heaviest one that is being used in the compression. Think of this like a JPG image and the video buttons. Then we have lab, a perception uniform code color space. Okay, so that is being used for color matching and perception task. Moving forward, and if you are imagining an RGB color, you can literally split it into R channel, G channel and B channel that separates gray color looking image, and you can stack them together. Okay, now for the boundary boxes, let me get you into a real meat of object detection, that is the boundary boxes. A boundary box is simply the tightening rectangle axis aligned, and meaning that it's not rotated, that's full enclosed an object. There are two common ways of it. One is the corner form. You store the top left and the bottom left corner, that's x min, y min, y max and x max. Center form, you store the center coordinate plus the height and width. Okay, so you'll be more clear with this when we'll be covering YOLO, that is you only look once. In that paper also it's written about that how these 4 5 6 parameters are so helpful for it. We have a matrix also, that is the intersection over union. This concept is probably the most important matrix in all of the object detection IOU, and intersection over union. So IOU measure that how well a predicted boundary box overlaps with the actual grounded truth boundary box. The formula is simple, that you take the area of overlap between the predicted box and the grounded box and divide it by the area of the union. Okay, now meaning that the total area being converged by both of the boxes combined. This gives you a number between 0 and 1. A value of 1 means perfectly overlapping, a value of 0 means no overlapping. In practical, a prediction is usually counted as correct or true positive if the IOU is greater than or equal to the threshold, that is being commonly 0.5. Now why does IOU matter so much? Okay, so because it's the foundation matrix for everything else in the detection. It defines whether the detection counts as correct in terms of localization or not. It drives the non-maximum suppression NMS, what is the process of removing duplication, overlapping boxes and everything, and it underlines the matches process to compute the precision, recoil and the MAP. Okay, now most importantly we'll be covering this precision and recoil again. This we have covered in the machine learning part also, but covering this again. So basically there are two matrices that we'll be covering in precision and recoil. For that we have a confidence threshold in the IOU. So we define true positive as a predicted box that matches a ground image with the IOU above threshold, and false positive is a box that doesn't match any ground image and either there is no ground truth there. So IOU is lower than the threshold and it's a duplicate detection. Next we have the false negative, a ground truth object that the model completely missed, no prediction matched it. Okay, so from these three numbers we can get the precision equal to the true positive divided by the true positive plus the false positive. Then recoil we have the true positive divided by the true positive plus false negative. Now we have another matrix, that is the mean average precision. Now the single most benchmark number in object detection, MAP, mean average precision. Here we go. First for one class we compute the average precision, AP. Now we swipe it across different confidence threshold, plotting precision against recoil and then calculating the area for the precision recoil curve. The area is the AP for the class. The MAP is simply the average of AP across all the class. In model benchmarks like COCO, it's also average across multiple IOU threshold, for example 0.5 to 0.95 in steps of 0.05. There are a few important variants for this. MAP at 0.5, you use a single lenient IOU threshold, that is a Pascal walk style. MAP at 0.5 to 0.95, averaged over 10 different IOU threshold. This reward model that localizes object very precisely. This is the COCO style and it's more rigorous standard today. AP small, AP medium and the AP large. They break down AP by the size of the object, so you can see that how well your model handles a small object versus the large one. Moving forward to one of the most important part, that is the annotation. So for the annotation format, before you ever train a detection, you need to label the data. Ground truth box is stored in a standard format. There are three domain format for it. COCO format, that's a single JSON file. Boxes are stored at X minimum, Y minimum, width, height in absolute pixel. COCO format comes with a rich metadata, segmentation mask, key points, categories, and it is widely used in the benchmark format. Then we have the YOLO format. This one is used as one text file per images. Boxes are stored at X center, Y center, and width and height, but normalized between 0 and 1 relative to the image. It's minimal and very fast to trace, but with a single line per object. We have VOC format also, that is also called as the Pascal VOC. This is being used the XML file per images. It's a human readable and the box are stored as X minimum, Y minimum, X max, Y max in an absolute pixel. So the key difference you can get from here. Now the annotation tools that we are using is these are being the some of them are the open sources and some are where you have to just take the dataset. For example, the RoboFlow, that's a cloud platform that handle the annotation and the data variation. You can click on any of the format, the COCO, YOLO, and the VOC format, and you can get the different model frameworks. You have the CVAT, that is the computer vision annotation tool. That's a browser-based support team collaboration. Video annotation with the frame interpolation can be done easily. You also have the labeling image IMG, label IMG. So it's a lightweight desktop GUI. It exports in either VOC XML or the YOLO TXT file. Okay. Now moving forward to wrap up this completely. So object detection require both classification, figuring out what something is, where it is localized, and figuring out about the position of that. So that's a fundamental difference between a plain image classification. Images are tensor, height times weight times channels, and the number of channels are the color spaces that you choose on how it can affect the extraction for the useful information. You have a IOU as the core matrix, and the other matrix are being defined from this only. Moving forward, MAP, that's the average AP score across the IOU threshold in the COCO style evaluating, and it's a standard single number used for the benchmark detection quality. You have COCO, YOLO, and VOC, that are the three domain annotation formats. They are mainly differ in the file structure and how the box coordinate are being represented absolutely versus the normalized. And tools like Label Image, CVET, and RoboFlow are what turns raw unlabeled images into proper training data. That's the essential step before you are training anything. And that's it for the foundation of the computer vision and the object detection. So we'll be covering this complete series with the everything for the autonomous side and the computer vision side. Okay, so thank you for this lecture.